The Earth's core is dying. Why scientists say our planet is turning off. Telemetry spikes, a satellite reboots mid-pass, and deep under Namibia clay pots. Remember a weaker field. Meanwhile, earthquake echoes whisper that Earth's inner core has slowed and begun backtracking. If the core is the engine, what happens when it stalls or just coughs? Here's the paradox. The shield that keeps our technology alive is tied to a churning metal ocean that doesn't run on schedules. Tonight, we'll trace the signal from repeating earthquakes to a dent in the sky and ask what a noisy geodynamo means for satellites, power grids, flyers, and us over the next 100 years. The 5 revelations you weren't supposed to see. 5 reveals. One story that starts with a quiet planet and ends with a checklist. First, the secret engine. Beneath your feet, a solid inner core sits inside a liquid iron alloy outer core. Heat leaks out, rotation twists flows, conducting metal cuts magnetic field lines and makes currents that reinforce the field. That self-sustaining loop, the geodynamo, builds a big dipole plus a mess of regional lumps. It's not a bar magnet, it's weather. Second, slowdown and reversal rumors, minus the hype. Seismologists stacked decades of repeating earthquakes that fire along the same paths. The tiny changes in core-crossing waves, PKEKP and its coda, say the inner core sped ahead for years. Then around 2009 to 2010, slowed and began drifting backward relative to the mantle. That's not Earth reversing, it's the inner ball shifting pace inside a sloshing outer core. The nuance matters. Differential motion, not doomsday. Third, the shield is already dented. Over the South Atlantic and Southern Africa, the surface field is weak. Satellites call it the South Atlantic Anomaly. There, the inner radiation belt sags closer to low Earth orbit. Instruments throw errors, star trackers blink, memory flips spike. ESA's swarm satellites watch the dent broaden and even split into 2 lobes. It's not fine, it's manageable if you plan like it's weather. Fourth, when the sky gets spicy. Space weather plus weak field equals overtime. A southward-aimed solar storm couples more energy into our system, inflating currents in the ionosphere and pushing geomagnetically induced currents along long power lines. Quebec 89, Halloween 03. Those aren't myths. Airlines reroute around polar blackouts. Satellites harden for deep dielectric charging. Operators widen SAA masks during storm days because the floor rises. Fifth, the horizon. Over 20, 50, 100 years, the likeliest track is more mess, not collapse. Global dipole modestly down since the early 1900s. Regional lumps louder, pole drift fast because the map is noisy, not because a flip is scheduled. Excursions, near misses, happen on century to millennia scales. Reversals take longer. The practical playbook wins. Harden memory, block jigs, diversify timing, and keep better watch on the core with satellites and ground arrays. Yes, it's complicated. So is your phone's battery health. Same vibe. Dying slower than your patience and still working tomorrow if you treat it right. We'll pop the hood next and meet the engine spinning in the dark. Because nothing says comfort like a molten metal ocean running our life support bubble. The engine in the dark. How the core makes a magnetic shield. To understand why a dent in the sky starts under our feet, go down past crust and mantle to a boundary where rock gives way to metal. At roughly 2,900 kilometers, seismic waves slow sharply. That's the top of the outer core, a global ocean of liquid iron alloy. Deeper still sits the inner core, a solid sphere of mostly iron and nickel, hot as a small star's photosphere and squeezed to metallic order. One phase sloshes, one rings like a bell. Together, they run a power plant that never sleeps. The energy budget is simple and relentless. Heat is escaping the planet. Primordial heat from formation, radiogenic heat from long-lived isotopes, and latent heat released as the inner core crystallizes grain by grain. Hot fluid rises, cooler fluid sinks. Rotation twists those motions. The Coriolis effect organizes the flow into column-like rolls aligned roughly with Earth's spin axis. Wherever a conducting fluid cuts across magnetic field lines, it induces electrical currents. Currents make magnetic fields, and those fields push back on the flow, steering future motions. That feedback loop is the geodynamo. It's not a neat bar magnet, it's weather in metal. The large-scale time-average field looks like a dipole. Field lines emerging near Antarctica, arcing through space and diving back down near the Arctic. But layered atop that global scaffold are regional lumps. Patches of stronger and weaker flux born from turbulent eddies, shear zones, and boundary conditions at the base of the mantle. The surface field we map is the sum of both, the elegant shape and the mess riding piggyback. 3 ingredients make the loop self-sustain. First, vigorous convection. Heat and light elements released as the inner core grows make buoyant fluid that wants to rise. Second, rotation. It organizes chaos into helical flows, the geometry a dynamo prefers. Third, electrical conductivity. Liquid iron alloys carry charge easily, so tiny currents amplify in the structure. Remove any one, cool the core too much, stop rotation, or replace iron with syrup, and the loop stutters. Mars likely failed that test long ago. Now, add the middleman that complicates everything, the mantle. It's solid on short timescales, but not uniform. Seismic tomography reveals 2 continent-scale thermochemical provinces perched atop the core, one beneath Africa, the other beneath the Pacific. Where the mantle above is hotter, it insulates. Heat leaks more slowly, and convection below slackens. Where it's cooler, heat escapes faster, and flow intensifies. That patchy heat flux imprints patterns onto the outer core's motions. At the core mantle boundary, you can map regions where field lines point up or down more strongly. Those patches drift, split, and merge over decades to centuries, dragging the surface field along. Meanwhile, the inner core does more than harden. Its growth releases latent heat and light elements into the outer core, fueling buoyancy. Some studies suggest hemispheric asymmetry in that growth, slightly more crystallization on one side, which would nudge convection patterns. Others see torsional oscillations, slow shear waves zipping through the outer core, briefly speeding and slowing zonal flow. Either way, the engine isn't static. It coughs, it clears its throat, it retunes. Why do we care? Because those tangled lines reach into space and grab charged particles by the collar. The magnetosphere, the vast magnetic bubble that envelops our planet, deflects most of the solar wind. Where field lines connect to space, currents flow along them, feeding auroras at high latitudes. Where lines close, they form traps, the Van Allen belts, where energetic particles spiral, mirror, and drift. The inner belt, rich in protons, sits closer to Earth where the field is strong. But the field isn't centered perfectly in the planet, so the belt sags lower over one sector, the South Atlantic. That sag is a downstream symptom of core complexity. The field also breathes with the sun. A southward interplanetary magnetic field locks onto Earth's day side, letting energy in. Reconnection in the tail flings plasma earthward, ionospheric currents surge, and the ground feels those changing fields as voltages induced along long conductors. None of that would matter without the core scaffold. It sets the stage, space weather writes the scene. Picture the loop in action. A plume of buoyant, iron-rich fluid rises along a column aligned with Earth's spin. Twisting motion wraps field lines into helices. Induced currents strengthen the poloidal field, the long arc from pole to pole, and generate a toroidal component, wrapped around like latitude bands. Shear and buoyancy exchange energy between those components in a cycle that keeps rebuilding the large-scale field even as turbulence scribbles on top. The math that captures this magnetohydrodynamics looks forbidding. The intuition is familiar: moving conductor, existing field, induced current, new field. We've tried to bottle that physics. In labs, researchers spin vats of molten sodium inside nested spheres and cylinders. The flows mimic helical motion, and sometimes, briefly, a magnetic field self-excites. It's finicky, too slow and nothing happens. Too fast and turbulence kills structure. But it proves the principle. Under the right conditions, motion begets magnetism. 2 final truths anchor this engine. First, it's resilient. The inner core's growth has likely strengthened the dynamo over the last hundreds of millions of years. Second, it's moody. Uneven heat flow and internal waves let regional features blossom for decades. That's how you get a weak patch over southern Africa that lasts long enough to matter for satellites, and long enough to leave a fingerprint in archaeological clay. So when a satellite reboots over the South Atlantic, that's not space being random. It's the end of a causal chain that starts in a metal ocean. The dent in the sky is the surface echo of weather in the core. And once you've seen the engine, the next question is obvious. What are the knocks and rattles telling us right now? Seismic whispers, what the core slowdown story really means. To hear the core, we listen to quakes that repeat themselves. Not the headlines, literal repeaters. Earthquakes that rupture on the same fault patches, send waves along the same great circle paths, and arrive at the same stations like clockwork. When the source and the path are nearly identical, the tiny differences left over, milliseconds shaved here, a faint wiggle there, become a microscope. The waves that matter for the core have an awkward name, PKIKP. Waves that go through the mantle, P, the outer core, K, pierce the inner core, I, then back out. Their coda, the faint ring down after the main arrival, carries extra hints about scattering and structure along the way. Now stack decades of those twins and the pattern changes. Through the 199s and early 200s, the PKIKP differentials behaved as if the inner core was super rotating, drifting eastward relative to the mantle by tenths of a degree per year. Then, somewhere around 2008 to 201, the sign flips. The differentials shrink, even reverse in phase. Studies that extended the catalog to 2023, adding fresh South Sandwich Islands repeaters and yes, Cold War nuclear test pairs as fixed reference shots, found the same story with better timing. The inner core didn't stop. It slowed relative to the mantle and began backtracking, moving westward more slowly than it had previously moved east. Think of two nested gears with a bit of slip. The outer gear, mantle, keeps turning. The inner gear, solid core, speeds up, then eases, then lags by a hair. The nuance matters. This isn't Earth reversing, it isn't even the whole core. The liquid outer core, the dynamo stage, is still sloshing. What's shifting is the solid inner core's tiny differential rotation relative to the crust and mantle above. We're talking minute angular rates on decadal cycles, not a cinematic grind to a halt. Media loves the core stopped, but seismology says it slowed and reversed relative to us, which is less viral and far more interesting. How do waves pick that up? Because iron isn't uniform at those depths. The inner core is anisotropic. Its crystals align preferentially, so waves going north-south travel at slightly different speeds than those going east-west. If the inner core's orientation or our relative angle through it changes, the travel time differences for core crossing phases shift. Repeating quakes keep the source constant. Any residual drift in arrival times points to changing geometry along the path. When multiple paths across Asia-Pacific, across the Americas, across the South Atlantic show consistent trends in PKIKP, meanest nearby core phases, a global signal emerges. The cleanest stacks show decadal modulation in step, with small wiggles in length of day. A hint that angular momentum is shuffling between the mantle and the core through electromagnetic and gravitational coupling. Why would the inner core backtrack? The same forces that spin it up can slow it down. Electromagnetic coupling. The magnetic field threading the fluid outer core can tug on the solid inner core. Topographic coupling. Tiny bumps at the inner core boundary. Mountains measured in hundreds of meters on a sphere the size of the moon can transmit torque as flows shear across them. If outer core flow reorganizes, say a torsional oscillation sweeps through, speeding and then slowing zonal motion, the net torque on the inner core changes sign. Over years, that nudge adds up to a phase drift we can measure as seismic time shifts. What nobody knew at the time was how much else had to be changing. Recent analyses suggest the inner core's surface itself may be evolving. Subtle changes in roughness or layering that alter wave amplitudes, not just arrival times. That doesn't rewrite the slowdown, it complicates the scoreboard. Seismology is honest about these caveats. We infer motion from a sparse network of precise but noisy observations and cross-check with multiple paths and methods. The convergence, repeaters, test shots, arrays, keeps pointing the same way. Speed up, slow down, gentle, reverse on a decadal beat. So, does a backtracking inner core mean a dying dynamo? No. The Geodynamo lives in the liquid outer core. The inner core's rotation tweaks torques and may modulate the dance, but it isn't the drummer. Picture a band where the bassist, inner core, occasionally lags the drummer, mantle, by a half beat, because the room acoustics outer core flow and magnetic coupling changed. The groove feels different. The song still plays. In fact, an inner core that can torque back and forth suggests an engine that's lively, not failing. Energy is still moving, coupling is still strong, and the system is elastic enough to exchange angular momentum without breaking its rhythm. What does tie this to our dent in the sky is timescale. The same decadal variability that nudges the inner core also shows up as geomagnetic jerks, abrupt changes in the rate of change of the magnetic field at Earth's surface. Those jerks ripple through observatory records, hinting that outer core flow reorganized. When it does, reverse flux patches at the core mantle boundary can wax or wane, and the surface field above southern Africa can weaken a little faster. The inner core's backbeat isn't the cause of the South Atlantic Anomaly, but it's part of the orchestra we're finally hearing clearly. Which brings us back to stakes. The Slowdown story isn't a countdown, it's a diagnostic. Every decade, the core coughs our instruments catch it faster. That makes forecasts less dramatic and more useful. And if the heart still beats, the shield can still scuff. So we head topside, where the dent already costs minutes, money, and patience. The shield has a dent. Inside the South Atlantic Anomaly, stretch a map from Brazil across the South Atlantic to southern Africa, and you're tracing the corridor satellites learned to fear. Operators call it the South Atlantic Anomaly, the SAA. On paper, it's a contour plot of lower magnetic intensity. In orbit, it's the 10 minutes per pass when instruments go dumb, star trackers see ghosts, and memory starts flipping bits like popcorn. Here's the mechanic, not the myth. The inner Van Allen belt, a torus of energetic protons trapped on closed field lines, rides closer to Earth where the magnetic field is weak. Because Earth's dipole is offset from center and tilted, that trap droops lowest over the South Atlantic. A satellite at a few hundred kilometers suddenly flies under the proton ceiling. Sensors designed for photons see particle hail. Error-correcting memory earns its salary. Whatever slips through trips watchdog timers. You see it later as black rectangles in data, planned science outages, because teams would rather lose frames than cook detectors. Hubble has a standing no science zone stamped over this longitude band. The International Space Station watches dosimeters tick higher and shutters sensitive experiments. CubeSats with thrift store shielding learn the hard way. One night, a student on console watches the attitude solution tumble into nonsense as a star tracker feeds corrupted centroids. The code falls back to gyros, reboots clean, survives. Nothing heroic, just standard life under a dented sky. The maps evolved. 2 decades ago, the anomaly looked like one blue bowl on an intensity plot. ESA's swarm satellites stitched a time-lapse. The basin widened, drifted west, then butted a second lobe to the east. That split matters because schedules hinge on minutes. A telescope that counted on a single window now dodges 2. Operators widen masks, shave exposures, and accept losses because the alternative is dead pixels and shortened mission life. It isn't only hardware. Flight surgeons track dose budgets for crews. The SAA isn't a crisis at current altitudes, but it raises the floor. Add a solar storm and the margin thins. Dispatchers slip polar routes south on bad days and plan EVAs to dodge predicted peaks. In the cockpit over the anomaly, a compass wanders a hair before the avionics vote it down. The system is built for this. Still, the dent turns routine into overtime. We like our villains clear, but the belt is only the delivery truck. The address is deeper. The surface field over the South Atlantic is weak, because the field at the core, mantle boundary beneath southern Africa, is tangled and in places reversed relative to the global dipole. That reverse flux patch drags the dipole off center and lets non-dipole features grow loud. The mantle piles above, one of Earth's deep thermochemical provinces, modulate heat loss and steer core flow, helping the patch persist. The dent in space is the last link in a causal chain that starts 2,900 kilometers down. You can watch the fingerprint in real operations. An ocean color imager returns a neat gap off Namibia, masked on purpose. A gamma ray instrument goes safe, then wakes with clean baselines. A ground analyst overlays reset events by longitude. A skewed cluster west of Africa, another east of Brazil, matching the twin lobes swarm mapped. Schedules look like airline timetables. Instrument off at 13:12. on at 1326. Every orbit, every day, nudged a little earlier each quarter as the centroid creeps. Altitude and inclination set how hard the SAA bites. Fly lower and drag trims proton energies. Fly higher and you clear the worst. There's a band where flux is just right to be a problem for popular orbits. Insurance actuaries know that band. So do procurement teams who argue for rad hard parts that weigh more and cost more and save missions quietly. One engineer swaps standard memory for a hardened part. The change adds grams and years. No trailer roll, just a flat error log the next storm day. The anomaly breathes with the sun. When a coronal mass ejection squeezes the magnetosphere and pumps fresh particles into the inner belt, the SAA's floor climbs. Teams widen masks and ride it out. This is why you see space weather on the whiteboard next to target lists. The Dent turns a solar forecast into a shift schedule. Here's the uncomfortable truth. The SAA is not waiting for you to finish your design review. It drifts, splits, and surprises. That's not bad news, it's a reality check. Treat it like weather, map it often. Fly with margin, harden what must stay on. Power down what can sleep. Keep a hand on the proton counter and a finger on the mask length, and remember where it starts. The Dent isn't a hole in space, it's the surface echo of magnetic
weather in a metal ocean under Africa. Deep roots, Africa's reverse flux patch and the mantle's hidden giants. Unknown to most people watching satellites hiccup over the South Atlantic. The mischief starts under southern Africa, at a boundary we can't visit, but can map by listening, and by ESA swarm inverted core field models. On the core mantle boundary, where liquid metal meets hot, solid rock, geomagnetists keep finding a stubborn blemish, a patch where magnetic flux points the wrong way relative to Earth's global dipole. It's not a tiny eddy, it's a continental-scale bruise that refuses to fade. In models that let the dynamo run, that reverse patch doesn't just happen anywhere. It blooms beneath Africa, where the mantle above isn't normal. Seismologists have a nickname for the giants parked there. Large, low, shear velocity provinces, LLSVPs. Two of them, one under Africa, one under the Pacific. They're not magma oceans, but they're hotter and likely compositionally different from surrounding mantle. So seismic waves slow down as they cross. Picture colossal, woolly plateaus slumped against the core, insulating some places while their steep edges leak heat like cracked radiators. That uneven heat loss, the how much and where, is the thermostat for the core's metal weather. Over Africa, the contrast is sharp. At the base of that LLSVP, heat trickles in one patch and pours in next door, setting up shears in the outer core's flow. Fast columns next to slow ones twist field lines into knots. In numerical dynamos forced with African-style heat maps, the same pattern repeats. A reversed flux patch forms beneath southern Africa, migrates, splits, then reforms. Up top, the surface field weakens in a lopsided bull's eye that lines up with today's South Atlantic Anomaly, as mapped by Swarm. The belt sag we dodge in orbit is the end of a story. The core started at that heated rim. This isn't modeling for modeling's sake. Rocks back it up. Archaeomagnetists collect fired clays, Iron Age pottery, and hearths from southern Africa and date them carefully. As those kilns cooled, tiny iron minerals locked in the local field. Layer a timeline of those directions and intensities across centuries, and you get repeated dips, episodes when the field over southern Africa was unusually weak and sometimes pointed askew. Offshore, South Atlantic sediments record the same softness. On the other side of the ocean, the salts in Brazil answer with directions that don't match a tidy bar magnet. Different materials, same theme. This sector misbehaves often. Meanwhile, swarm-class inversions peel off the ionosphere's daytime loops and the magnetosphere's storm surges to reveal the core's baseline. Those maps show reverse flux intensifying beneath southern Africa, riding westward drift and feeding the surface dent we fly through. Seismic tomography stacks, thousands of earthquakes marching through Earth, trace the African LLSVP's bulbous top and steep sides. Put the pictures together and a loop emerges. Deep mantle structure modulates heat. Heat patterns steer core flow. Core flow breeds a reverse patch. The surface above weakens. The inner belt droops. Satellites feel it. There's still a fight over identity. Is the African LLSVP mostly hot, or also chemically distinct enough to be denser and long-lived? The answer matters for timelines. A purely thermal blob might evolve faster. A thermochemical pile could persist for hundreds of millions of years, making its magnetic influence a recurring character in Earth's story. Right now, the best fit is both. A long-lived pile with thermal hills and valleys that wax and wane. That mix would explain why the reverse patch keeps coming back under Africa while still breathing on decadal scales. The models also explain why this neighborhood matters in reversals and near misses. When dynamos flip in simulations, big reverse patches often grow first at LLSVP margins, eroding the dipole until the field goes multipolar. Extra poles sprouting at odd latitudes before reorganizing opposite. Earth's record shows excursions like Laschamp, a dramatic weakening without a full flip. Southern Africa shows up there too, an early stage where weakness concentrates. Not a guarantee, a habit. The human part looks small and precise. In Cape Town, a grad student carries sherds from a dig to a shielded room, heat treats them in tiny steps, and watches magnetization curves hold steady at low intensity. Across town, a modeler nudges the heat flux at the African LLSVP's edge and watches a reverse patch in their simulation wrap farther around the core. They tape plots side by side, clay and code, and write close in pencil. That one word is how disciplines meet. The stakes are practical. If the African patch is a persistent engine for surface weakness, the SAA isn't a one-off. It's the present face of a long pattern. It will drift, split, and surprise, but it probably won't vanish on a schedule we prefer. That doesn't mean
panic. It means treating magnetic complexity like weather. Keep the core maps fresh, harden what must stay awake, mask what can sleep, and remember the causality. The dent is a surface echo. The source is a giant, lumpy blanket under Africa, telling the core where to race and where to rest, and telling us how to fly. Space weather meets soft shield, why storms hit harder. While that reversed patch simmers under Africa, the sun writes the plot twists. It doesn't whisper. It shouts in X-rays, hurls coronal mass ejections, and twists magnetic ropes until they snap. Most days, Earth's field handles it. On some days, configuration is destiny. The interplanetary magnetic field tilts south, locks to Earth's day side like Velcro, and energy pours in. With a softer, lumpier shield, more of that energy sticks where we least want it. Start with the solar cycle. Roughly every 11 years, the sun ramps up. More sunspots, more flares, more CMEs. A halo CME heads our way, and a forecaster sees the ring expand in a coronagraph. The clock starts. If the CME's magnetic field points south when it arrives, reconnection on the day side swings the door wide. The magnetotail stretches, snaps, and slings plasma toward Earth. Field-aligned currents roar into the auroral zones. Beauty overhead, trouble beneath. Why a weak field makes it worse is geometry. Where intensity is lower, coupling is easier. The same solar wind pressure pushes field lines deeper. The ionosphere over weak regions hosts stronger currents. Those currents close through the ground, and long conductors act like antennas. Utilities call them geomagnetically induced currents, GICs, and their DC-like biases, transformers hate. Push a core into partial saturation, and it heats, hums, distorts waveforms. Protective relays misread the moment. Quebec, 1989 was exactly that. A fast cascade from space weather to a province in the dark in under 2 minutes. Now put that physics on a dented map. Over the South Atlantic and Southern Africa, lower field strength means ionospheric currents can be beefier for the same solar storm. A utility planner in Johannesburg watches neutral currents rise on a station display. No one bothered to install in the 199s. They shed transfers across a long corridor, bring local generation up, and ride the night without a headline. Somewhere else that didn't budget for monitors, a transformer runs hotter than design and loses a few years of life in 8 hours. Satellites feel the same story in a different language. Storm time injection pumps energetic electrons deep. The outer belt puffs, the slot region fills, and low Earth orbit sees flux levels that turn minor annoyances into flurries of upsets. Deep dielectric charging is the sneak thief. Electrons bury in insulation and discharge later as a miniature lightning strike inside electronics. Star trackers lose stars in scintillation. GPS receivers see phase scintillation and drop lock. Timing chains hiccup. Teams widen South Atlantic masks because the floor rose, and the dent now covers minutes that weren't risky yesterday. Aviation lives between the two. At flight levels, cosmic ray dose ticks up during storms. Polar routes, always nearer to the open field lines, take the hit first.
HF radio goes patchy. Dispatchers route south, burn more fuel, and reset crew duty days. Over the South Atlantic, a moderate storm plus a weak patch means a higher baseline dose and a few minutes of degraded nav. The airplane shrugs because inertial plus DME still works. The crew logs, HF weak, GPS integrity flagged, reverted automatically. Annoying, not cinematic. Multiply by 1,000 flights and it's a day of overtime. This was the moment everything changed, when operators stopped treating storms as surprise and dense as trivia. Space weather centers now push tailored alerts. Arrival window, expected southward field, KP forecasts, confidence. Grid operators rehearse playbooks the way coastal towns practice hurricane evacuations. Stage 1, limit long-haul transfers. Stage 2, watch neutral currents. Stage 3, block DC with series capacitors and neutral blocking devices on vulnerable corridors. Restore when magnetometers quiet. Satellite control rooms run storm configs. Raise detector thresholds. Expand SAA masks. Scrub memory faster and accept science losses to save hardware. Meanwhile, better eyes matter. Upstream solar sentinels at L1 tell you shock arrival an hour ahead. Multi-longitude coronagraphs improve CME direction and speed. Magnetometers across continents feed real-time GIC estimates. Downstream, ESA's swarm-class successors update the core field, so storm impact models aren't flying blind over a decade-old map. Data assimilation, borrowed from weather, stitches it together into nowcast the night shift can trust. Bottom line, it's not apocalypse, it's overtime for operators. Weak field regions don't doom technology. They shorten margins and punish denial. Hardening buys years, forecasting buys hours, drills buy calm. The sun will keep throwing punches on its own clock. The core will keep breathing on its own. Our job isn't to stop either. It's to keep the lights on and the spacecraft alive while a dented shield does what it's always done. Deflect most of the storm and make the rest our problem. Reversals and near misses. How the field actually flips. To see a flip begin, shrink the tidy bar magnet in your head into a crowded room argument. The big dipole is the loudest voice, but smaller magnetic eddies shout from the corners. When those side conversations grow, the main voice falters. The choreography isn't a switch, it's a slow unseating. First, the dipole weakens, then extra poles pop up in awkward places. And only after a long, messy debate does a new dipole take the microphone, sometimes pointing the other way, sometimes the same. The timeline lives in rocks. Cool a lava flow, and tiny iron minerals lock the ambient field. Stack flows across continents, and you get a pulse. Long spells of normal or reverse polarity, punctuated by irregular intervals. Between full flips sit excursions, near misses, where the field collapses to a fraction of its strength. Directions wander, auroras stray equatorward, and then the original polarity wins back the map. Laschamp, about 41,000 years ago, is the poster child. Intensity fell to roughly 5 to 10% of today's directions, lurched for centuries. Then the dipole reasserted itself. The playbook repeats. Opening act, dipole down. Not zero, weak. While it fades, non-dipole features swell. Regions already prone to mischief, like the sector above southern Africa, become staging grounds. At the surface, weak zones spread and sometimes split. In the air, navigation that leans on a calm model notices more noise, not nonsense. Compasses still point generally poleward, they just meander. In the sky, geomagnetic storms couple more efficiently in those soft spots, so auroras ride farther from the poles on bad nights. If a true reversal follows, the middle axis gets strange. Multiple poles coexist. Local maxima wander across latitudes like musical chairs. Field lines dive in Sahara latitudes and emerge near Indonesia, while the canonical north-south axis collapses into a multipolar quilt. Paleomagnetic traces call this the transitional field. It isn't globally uniform and it isn't brief. Hundreds to a few thousand years pass as the system reorganizes. In an excursion, that transitional chaos retreats. The dipole strengthens, the extra poles fade, and the map looks boring again, until the next stumble. Why the African neighborhood matter shows up in both data and models. Reverse flux patches at the core mantle boundary beneath southern Africa often blossom early in simulated flips. In Earth's record, southern African clays and South Atlantic sediments record repeated intensity dips and odd directions,
right where today's Dent rides. Not because a flip is scheduled, but because the same boundary forcing keeps seeding the same kind of trouble. Reversals don't always start there, they often rehearse there. Timescales keep us honest. From the first broad weakening to a clean opposite dipole, you're counting centuries to a few millennia. People live, build, and argue under skies that look mostly normal. Technology feels it first because we depend on details. Satellite hazard zones no longer sit neatly over one ocean. SAA like Dent sprout elsewhere, drift, and merge. Models that forecast radiation risk update like weather charts. Grid operators see more GIC-prone nights during solar peaks. Airlines routinize space weather detours. None of it is apocalypse. All of it is logistics. Mechanically, the flip is a connectivity problem. The dynamo keeps generating both poloidal and toroidal fields. When reverse patches spread enough to choke the global dipole circuit, the system falls into a multipolar state. From there, small asymmetries, sustained by heat flux patterns at the core's top, tip the network into a new coherent dipole. It isn't inevitable which way wins. Change the forcing a little, and an excursion aborts the transition. Nudge it the other way, and a reversal completes. Same physics, different end states. Life's receipt for past flips is underwhelming if you want drama. No mass extinction badge for magnetism. Ozone chemistry likely nudged in patches during weak spells, raising UV a little under clear skies. Low-latitude auroras probably stunned night watchers who left no captions. The atmosphere did most of the shielding work it always does. The stakes today run through wires and orbits, not lungs and leaves. So if you hear reversal used like a countdown, translate it to a calendar. What's plausible is not a day when compasses twirl and satellites die, but a long, noisy middle where the map gets complicated. That middle is navigable by hardening, by forecasting, by treating the field like weather with history. And if you want to know whether we're headed there soon, you don't look for a prophecy. You keep watching the core, the dent, and the sun, because the next twist will arise from all three sharing the same room. Is the field really weakening, and how fast? So strip the drama and count the volts. The cleanest picture comes from a marriage of satellites and old-school observatories. On the ground, a century of stations watch declination, drift, and intensity creep. Overhead, Orsted and Champ tightened the map in the 2000s. ESA Swarm has been stitching a time-lapse since 2013. Modelers peel off daily ionospheric loops and storm wiggles from the magnetosphere. What survives is the core's baseline, changing like a slow tide. On that baseline, the global dipole, the bar magnet part, has declined roughly 10% since the early 1900s. Not a cliff, a slope. Some decades ease, some steepen a hair, but the trend line tilts down. Meanwhile, the lumps got louder. Non-dipole structure, the regional bumps and bruises, has gained weight, especially over the South Atlantic and Southern Africa, per ESA's Swarm time-lapse. That's why pole drift sped up. The needle chases a bumpier map, not a collapsing one. Zoom in and the story gets lopsided by design. North America and parts of Asia lost strength gently. The South Atlantic bled faster. Swarm's movies show the SAA darken, stretch, split into two lobes, and creep west-southwest. Engineers feel that as schedules shaved by minutes each year, the average pilot doesn't. That contrast is the point. Technology cares about local gradients. Your front porch does not. Is it accelerating? Ask 3 scientists and watch them reach for window length. Over 20 years, you catch the SAA split and think faster. Over a century, the dipole looks steadier. Even the rate of change has sudden jolts, geomagnetic jerks, where the slope shifts without committing to a long-term gear. That's why papers talk in curvature and confidence bounds, not prophecies. Short windows mislead. Long windows blur detail. We live between them. What about those sprinting poles? Magnetic north raced across the Arctic in recent decades. That's a symptom of a messier field, not a doomsday clock. When regional features bulk up, the pole, defined by where the field points straight down, jumps toward whichever lump is loudest. Models reproduce that behavior without flipping. It's weather, not verdict. Here's the nuance that saves budgets. A trend by itself is housekeeping. A trend plus a storm is a risk recipe. A modest dipole makes it easier for a southward CME to couple energy into our system. That doesn't turn every Tuesday into Quebec 89. It means the same solar punch buys a little more leverage, especially over weak field corridors. Grid planners translate that into transformer headroom and neutral current monitors. Satellite teams translate it into shielding around memory and wider South Atlantic masks on active sun days. Forecast beats fate. Uncertainty isn't an excuse to shrug, it's a scope. Inversions carry error bars because separating core signals from space weather requires assumptions about sources and timing. Swarm's 3-satellite geometry helps, but models still publish ensembles, many fields that all fit the data, bracketing the wiggle room. Across those ensembles, 2 truths survive. The dipole is down modestly on century scales, and the non-dipole field is noisier, with a persistent weak zone over the South Atlantic. Does that mean a flip soon? Paleomagnetism says no clock. The rock record is full of century to millennium dips that didn't end in reversals. Excursions happen, reversals are rarer and slower. The present configuration, dipole down, African reverse flux patch loud, SAA sprawling, looks like a precondition for messiness, not a guarantee of an outcome. The responsible sentence is boring and useful. Expect more complexity, plan for storm days, keep watching. Meanwhile, models keep getting better because the inputs do. Annual core field updates, new ocean bottom magnetometers to fill blue gaps, solar sentinels that nail CME timing and orientation. Each upgrade turns a vague curve into a usable forecast. Utilities fold that into drills. Constellations price it into insurance. Flight ops add it to dispatch screens next to winds and turbulence. The takeaway isn't collapse, it's calibration. The field is weakening globally, faster regionally, and changing shape in ways that matter for machines before people. The clock runs in decades. The spikes arrive in hours. If we treat magnetic complexity like weather, measure, model, mitigate, the next 100 years are more maintenance than melodrama. The human angle, satellites, flights, grids, and you. Start in a quiet control room at 2 a.m. A mission ops lead watches the orbit trace slide toward the South Atlantic Anomaly. She's already uploaded a storm day config. Detector thresholds higher, memory scrubbing faster, an extra 90 seconds of SAA mask. The proton counter climbs, the spacecraft naps on purpose. 10 minutes later, it wakes healthy. The only sign of the dent is a neat rectangle of zeros in tomorrow's dataset, and a team that goes home on time. That rectangle is the cost of doing business in low Earth orbit. Designing for a noisy shield begins with parts. Radiation-hardened memory resists bit flips. Triple modular redundancy lets 3 brains vote out a liar. Watchdogs reboot misbehaving processes before they spiral. It adds mass and money. It also buys years. Star trackers carry playbooks. When particle hits, turn the sky into static handoff to gyros, coast, reacquire. Instruments learn to blink on the Dent schedule. Schedules evolve because the Dent does. Operators tune masks quarterly as the lobes drift. During solar peaks, they widen them again. Quiet logs on storm nights are the win. Not everything can sleep. Communication satellites, weather birds, and timing nodes must stay awake. Those designs push shielding around the crown jewels: clocks, power electronics, and interfaces. Deep dielectric charging, the slow burrow of electrons into insulation, gets a seat at the table. Engineers add purge cycles and guard rings. Insurance pricing follows orbit and inclination like weather maps. Constellations spread risk across many identical spacecraft. One failure is a blip, not a crisis. The lesson is simple. Harden what must survive. Choreograph the rest. Drop to 39,000 feet. In the cockpit, redundancy isn't a slogan, it's architecture. Flight management computers cross-check sensors. If a single event upset flips a bit in one box, 2 others vote it down. GNSS integrity flags. The system slides to inertial plus radio nav aids without asking permission. Pilots note a second's worth of compass wander near the anomaly and move on. Real work happens at dispatch. Space weather advisories slide polar routes south during storm watches. Dose management for crews is tracked like hours. Pregnant pilots get different pairings. Over the South Atlantic on a quiet day, you don't feel anything. On an active day, you might hear more HF static and see a timing caution. The checklist hasn't changed. Aviate, navigate, communicate, now with a weather page labeled Space. Cabin health is measured, not guessed. Dosimeters ride in galleys and on bulkheads. Regulators set conservative limits. Airlines spread exposure with scheduling. The headline truth is dull and kind. A transoceanic flight adds microsieverts. A CT adds millisieverts. The outliers are storm days. That's why dispatchers watch the sun and why EVAs on station avoid predicted peaks. The SAA raises the baseline a notch. The sun adds the spikes. On the ground, the language is currents and transformers. Utilities learn the hard way that long lines make big antennas for geomagnetic storms. Today, they install neutral current monitors at substations, build real-time GIC dashboards, and rehearse playbooks. Stage 1, reduce long-haul transfers. Stage 2, bring local generation online. Stage 3, block DC with series capacitors or neutral blocking devices on vulnerable corridors. New transformers get thicker cores for extra thermal headroom. Spare programs and regional sharing agreements turn months of outage into days of inconvenience. You don't see the win because nothing fails. Somewhere, on a storm night, a neutral current trace rises and then flattens because someone flipped the right switch an hour earlier. Navigation and timing are the glue between space and ground. When the ionosphere ripples, GNSS errors spike. Critical systems hedge. Multi-constellation receivers take all 4 fleets. Fiber-based timing feeds, data centers and cell towers. Local holdover clocks ride out a bad hour. Aviation stays sharp by practicing degraded nav procedures. Surveyors schedule around KP, forecast the way photographers schedule around clouds. What about you? Most of this vanishes into routine. Your maps still load, your flight lands, the lights stay on. When they don't, it's usually weather with rain, not weather with protons. The preparation behind that normal day looks like boring decisions. A satellite designer swapping an ECC memory, a program manager signing for a kilogram of shielding around a clock can, a grid operator shaving load across a corridor to keep a transformer cool, a dispatcher moving a line of flights 20 minutes later to dodge a space weather watch. None of them fix the core or the sun, they fit people into the middle, and that's the point. A dented shield doesn't demand heroics, it demands discipline. We harden, we forecast, we drill, we accept trade-offs. We treat magnetic complexity like weather, measured, anticipated, and budgeted. The return is as invisible as a quiet log. The next section asks how we keep that vigilance sharp, how to watch the core in near real time, so tomorrow's rectangles of zeros stay rectangles, not epitaphs. Watching the core in near real time. To keep tomorrow's rectangles of zeros from becoming obituaries, we watch the engine while it runs. The trick is seeing a metal ocean you'll never visit through signals that hate to be clean. Start with secular variation, the field's slow drift in direction and strength. Ground observatories log it daily, satellites stitch it globally. Strip off the ionosphere's daytime loops and the magnetosphere's storm spikes, and what's left is the
Core's handwriting, changing like a tide. Inversion is the art that turns scribbles into maps. Modelers take vector measurements from swarm-class satellites, blend them with century-long ground records, and solve backward to estimate the field at the core mantle boundary. Out pop features that look alive. Reverse flux patches waxing and waning, westward drift marching like a conveyor belt, and a stubborn blemish under southern Africa that keeps feeding the South Atlantic Dent. It's not guessing. It's physics plus data, with error bars that say where to trust and where to squint. Then we push one step deeper. Core flow inversions. If the field is evolving this way, what motions in the outer core could produce it? The answer isn't unique, so teams run ensembles. Many plausible flows that all fit the observations. Across them, themes repeat. Columnar rolls aligned with rotation, shear zones at LLSVP edges, torsional oscillations that sweep like slow pulses. You don't see the liquid move, you see its fingerprints, and that's enough to plan. Seismology adds a second set of eyes. Earthquakes send waves through everything. How those waves speed up or slow down sketches structure. Stack thousands, and the mantle's giants appear. The African and Pacific LLSVPs, tall plateaus slumped atop the core. Their steep rims leak heat faster, steering flow below. Meanwhile, inner core seismology, those repeating PK-AKP paths, keeps time on decadal beats, catching the inner core's gentle backtracking that hints at changing torques. One discipline maps scaffolding, the other tracks tempo. Data assimilation is where it becomes weather-like. Borrowed from meteorology, it blends measurements with dynamo models in near real time. New satellite passes nudge the solution. Ground stations anchor trends. Physics fills the gaps. The output isn't a static chart. It's a living state estimate with uncertainties. updated on a cadence operators can use. When a geomagnetic jerk snaps the slope of change, the system flags it fast, and planners widen masks or tweak storm models before it hurts. Eyes upstream matter too. Solar sentinels at L1 tell you when a shock will hit in an hour. Multi-longitude coronagraphs tighten speed and direction. New imagers infer a CME's magnetic orientation, the difference between interesting and plug in the neutral blockers. Fold that into coral-aware impact models, and a storm forecast stops being a shrug. It becomes a timetable with names, which corridors, which orbits, which minutes. We're filling blind spots. Ocean bottom magnetometers extend coverage into blue deserts. Polar superstations tie upper atmosphere currents to ground responses. Absolute magnetometers on new satellites drift in local time to separate external and internal fields more cleanly. Continuity is the quiet hero. A gap kills trend confidence. A successor mission turns a line into a movie. Micro-stories keep the scale human. In Hermanus, a tech recalibrates a century-old variometer and smiles at a milligauss offset that matches last year's model. In Darmstadt, a data engineer rejects a swarm pass because a substorm snuck into the subtraction. The core movie mustn't blink. In Toulouse, an analyst overlays tomorrow's SAA lobe on a telescope's time window and slides an exposure by 4 minutes. No drama, just foresight buying boredom. Frontier questions steer the next upgrades. How asymmetric is inner core growth, and on what cadence does it modulate outer core flow? How sharp is the African LLSVP's rim, and how stable is its heat flux contrast? Do torsional oscillations leave fingerprints we can track on 5 to 10 year cycles to predict jerks? Each answer tightens forecast windows from vague decades to useful years. Remember the point. Better watching doesn't stop storms or silence the core. It shrinks uncertainty and lengthens lead time. That's the difference between a dead detector and a neat rectangle of zeros. Between a hot transformer and a flat neutral current trace. Between a headline and a yawn. The engine runs in the dark. Our job is to keep the lights on while we read its pulse.
Scenarios for the next 100 years. Think in paths, not prophecies. 4 tracks capture the next century, each with a budget, a headache, and a way to win. First, the baseline. Modest dipole decline, louder regional lumps, the South Atlantic Anomaly widening, splitting and drifting west. Satellites treated as moving weather. Operators widen masks by minutes each year, harden memory and power electronics, and ride storm days with conservative configs. Aviation folds space weather into dispatch dashboards, slipping polar tracks south when advisories light up in logging dose with the same discipline as duty time. Grids practice night shifts where neutral currents climb and flatten because someone threw the right switches early. Boring by design. That's the likely case. Second, stabilization. Core flow reorganizes, the dipole slide eases, and the SAA's lobes merge or slow. It's happened before on century windows. Nothing resets to 195, but margin returns a notch. Prep invested now still pays off. Shielding doesn't expire. Series capacitors don't regret blocking DC. Forecasting doesn't retire. The tone shifts from emergency to maintenance. Think brake check, not engine swap. Third, an excursion. The field's bar magnet part halves or thirds across centuries. Non-dipole features blossom, and SAA-like dents show up at new longitudes. Not a flip, a near miss with consequences. Storm years bite harder. Satellite attrition rises unless designs assume a higher particle floor. Constellations mitigate with numbers. Flagships survive by being conservative. Aviation routinizes space weather reroutes. GNSS gets noisy more often. Critical systems lean on fiber timing and holdover clocks. Grid size for G3, G4 nights as normal, bad. Not once in a career. Survivable, costly without rehearsal. Fourth, a full reversal inside a century? Low probability. If it begins, we live in the messy middle. Multipolar fields, migrating weak zones, and frequent pole meanders. The sky looks fine most days, the maps don't. Practically, it's the excursion path stretched. More dents, more drift, more updates. The point stands, logistics, not lore. Timelines keep everyone honest. Satellites live 5 to 15 years, so choices made this quarter fly into the next solar peak. Grids turn over in decades,
Transformers are ordered in years and replaced in months if you stock spares. National infrastructure plans in multi-decade arcs. That mismatch is why we translate deep time into program cycles. Build what helps now and can be extended later. Sector by sector, the checklist is painfully concrete. Space, rad-tolerant memory and logic, configuration scrubbing, deep dielectric mitigation, and SAA-aware autonomy that adapts as lobes drift. Harden clocks and power electronics. Fly constellations where you can, and accept planned rectangles of zeros over the Dent as asset protection, not failure. Fold storm forecasts into ops the way you already fold reaction wheel momentum dumps. Air, dose-aware dispatch and crew scheduling. Training for degraded GNSS and HF outages. Diversified comms links across SATCOM, VHF, and procedural separation when HF dies. Equip aircraft with real-time dose monitoring and integrate that readout with flight management. Treat space weather advisories like turbulence. Not scary, just another page to brief. Grid, install JIC monitors on long corridors, add series capacitors or neutral blocking devices, increase transformer thermal headroom, expand spares and sharing agreements, and run drills keyed to storm plus weak field scenarios, not just the last famous storm. Build real-time models that ingest magnetometer networks and neutral current sensors to route power around hotspots before copper smells funny. Timing and positioning. Multi-constellation receivers plus fiber timing backbones. Resilient, authenticated time distribution. Local holdover clocks with hours to days autonomy. And site surveys that record ionospheric sensitivities. In a noisy ionosphere, redundancy beats faith. Science. Fund swarm-class successors with drifting local times. Maintain ground observatories and add ocean-bottom magnetometers. Fly solar sentinels that constrain CME timing and magnetic orientation, and expand data assimilation so operators get core-aware, storm-aware nowcasts. Continuity is a strategy. A gap kills trend confidence. A successor mission turns a line into a movie. Policy is the multiplier. Require space weather margins in procurement. Align utility regulators with GIC mitigation budgets. Standardize aviation playbooks across regions so a CME doesn't become a patchwork of improvisations. Make space weather alerts as routine as winter storm warnings. Insurance can nudge designs the last mile. Premiums that reward hardening and ops that follow advisories. Bonus: fewer 3 a.m. panic calls. Best case in 100 years, we yawned through a couple of strong cycles because forecasting got sharper and hardware grew a thicker skin. Baseline: more masks, a
Few rough storm nights, and a lot of drills that look silly until they save money. Excursion: noisy decades that still land planes, keep telescopes alive, and leave cities lit because people treated magnetic complexity like weather. Full reversal in that window? Plan for the middle acts, not an ending. It's not a movie jump cut. It's a very long group project. The engine will keep coughing, the sun will keep shouting. Our part is discipline, hardware, procedures, and patience, paid forward in quiet logs, myths, hype, and what we actually know. Let's kill the campfire stories that refuse to die. Myth 1. A flip is an instant apocalypse. Reality: reversals and excursions unfold over centuries to a few millennia. The dipole weakens, extra poles pop up, then the system reorganizes. There's no day when compasses spin wildly and satellites all die at once. Risks rise unevenly and mostly during solar storms. With planning, it's overtime, not extinction. Myth 2. The South Atlantic Anomaly means a flip is imminent. The SAA is a regional weak zone tied to a stubborn reverse flux patch under southern Africa, modulated by the mantle's giant thermochemical pile. Versions of this have appeared before without triggering flips. It's a design constraint for orbits, not a countdown clock. Myth 3. A weaker field disappears. Even in low phases like Laschamp, Earth still had a field. The atmosphere kept doing most of the shielding at the surface. Aviation dose ticked up in our modern analog storms. Technology felt it first. People continued living under slightly stranger skies. Myth 4. Magnetic north racing across the Arctic proves collapse. Pole sprint is a symptom of a bumpier field, not a timer. Models reproduce fast pole drift in non-flipping states. Interesting? Yes. Predictive? No. Myth 5. The core stopped. Seismology shows the inner core's differential rotation slowed and began backtracking relative to the mantle around 201.
That's a gentle phase drift on decadal beats, not a global break slam. The dynamo lives in the fluid outer core. The inner core modulates, it doesn't power the engine. Now, the hype that sells end of civilization blackouts from a flip. The recipe for real trouble is a weak, lumpy field, plus a southward CME that couples hard. We've seen the bridge, Quebec '89, Halloween 2003. What changed is posture. Utilities install GIC monitors, add series capacitors, and rehearse storm ops. Satellites harden memory and power, widen SAA masks on active days, and accept planned gaps. Aviation dispatch routes like it routes around turbulence. The drama is in the budget, not the sky. What we actually know rests on three pillars. First, observations. Orsted, Champ, Swarm, and century-old observatories converge. The global dipole is down roughly 10% since the early 190s. Non-dipole structure is louder. The SAA expanded, drifted, and split. Second, seismology. Repeating earthquakes and even vintage test shots show the inner core's relative rotation slowed and reversed gently. Separate work hints its surface may be evolving. Third, deep earth structure. Seismic tomography maps the African LLSVP's steep edges. Core field inversions park reversed flux beneath it. Archaeomagnetism from southern African clays records repeated weak spells. The chain hangs together. Mantle thermostat, core flow, reverse patch, surface weakness, belt sag, operations. Unknowns are real. We infer flow from changing fields with error bars. Heat flux patterns at the core. Mantle boundary aren't mapped directly. Inner core growth asymmetry and torsional oscillations are active research. Forecast skill fades with time. Beyond a few decades, scenarios beat dates. That's why responsible language sounds boring. Elevated odds of messiness, not a guaranteed flip. So trade the myths for operating truths. Trend alone is housekeeping. Trend plus storm is risk. Regional weakness moves minutes on satellite masks and margin on grids. The human lever is prep. Harden what must stay awake. Schedule what can sleep. Monitor currents. Drill storm nights. Keep the core movie fresh. And listen to space weather like you listen to winter fronts. 2 short, useful sentences to keep. The field is weakening modestly, and the map is getting bumpier, especially over the South Atlantic. Prep beats panic every time. Because the engine under Africa will keep coughing, the sun will keep shouting, and our job is to keep turning those noises into schedules, not headlines. Next, we turn that posture into a playbook. Hardware, forecasting, and habits that make magnetic weather feel like weather. The playbook: hardening, forecasting, living with a noisy shield. Treat magnetic weather like weather. That means 3 habits. Build tougher hardware, get better forecasts, and live by procedures that turn surprises into schedules. Start with space. Radiation is statistics, so design for it. Memory wears armor first. Error-correcting code has table stakes. Then configuration. The quiet janitor that rewrites flip bits before they cause a scene. Triple modular redundancy lets 3 brains vote and exile the liar. Power electronics get guard rings and crowbar circuits that dump transients before they cook a board. Deep dielectric charging is the sneak thief. Purge cycles and shielding around long cable runs keep electrons from nesting in insulation. Clocks are crown jewels. Wrap them in mass. Add a second clock, then a third. Make sure they disagree politely before they drift. Autonomy learns the Dent's choreography. SAA-aware software stretches mask automatically as lobes drift, shifts instrument thresholds on active sun days, and hands star trackers off to gyros before static drowns stars. Accept rectangles of zeros as longevity, not loss. Fly constellations when you can. Many small satellites with graceful failure beat one hero with a grudge. Price insurance the way you price turbulence, by orbit, inclination, and season. Aviation's hardening looks like redundancy and practice. Build sensor diversity into navigation. GNSS from multiple constellations plus inertial and radio nav aids. When the ionosphere gets wobbly, the airplane slides to inertial without drama and checks back later. Diversify comms. HF for polar, SATCOM, and VHF everywhere else. Treat space weather advisories like icing. Route around, slow down, brief the crew. Dose management gets concrete. Real-time monitors and cabins feed dispatch.
Crew schedules spread exposure and EVIS thread between predicted peaks. Nothing heroic, just measured risk. Grids play defense with measurements and switches. Install neutral current monitors on long corridors. Build real-time dashboards that blend magnetometer data with local currents. Pre-stage generation for storm nights. Hardware buys margin. Series capacitors and neutral blocking devices keep DC-like jigs out of transformer cores. Bigger thermal headroom buys time. Spares and regional sharing turn months into days. Drills do the rest. Storm scripts, stage 1 through stage 3, live on clipboards and muscle memory. Forecasting is the multiplier. Upstream, more, and better eyes on the sun. Coronagraphs at multiple longitudes to nail CME direction and speed. L1 sentinels for arrival clocks. Imagers that infer a CME's magnetic orientation. The difference between interesting and plug-in the blockers. Downstream, core-aware models reduce surprise. Swarm-class successors drift in local time to separate external and internal fields. Ocean-bottom magnetometers fill blue gaps. Ground observatories keep the century-long time series honest. Data assimilation glues it together into nowcast operators' trust, where the ionosphere will ripple, which latitudes will host stronger currents, which minutes to mask across the dent. Policy makes the habit stick. Procurement bakes space weather margins into satellite specs. Regulators give utilities room and obligation to install GIC monitors and blocking devices. Aviation authorities standardize space weather routing the way they standardize RVSM and RNP. Insurance nudges designs the last mile by rewarding hardening and punishing magical thinking. The daily rhythm changes quietly. A telescope pi sees an alert, slides an exposure by 4 minutes, and keeps the detector clean. A constellation ops lead widens masks an extra 90 seconds for a week, then dials them back. A dispatcher shifts a polar bank 20 minutes later, logs dose, and moves on. A grid operator flattens a neutral current trace with a switch they tested last quarter. The win is a boring night. Science isn't an ornament, it's maintenance. Fun continuity. No gaps after swarm, no dark years upstream. Push frontier questions only when they feed lead time. How sharp the African LLSVP's rim is. How torsional oscillations time geomagnetic jerks. How intercore growth asymmetry modulates torque. Each answer compresses uncertainty and buys someone a schedule instead of a scramble. And culture is the hinge. Reward teams for rectangles of zeros that save detectors. Celebrate the non-event, the transformer that didn't run hot, the satellite that lived its design life, the flight that landed on time through a storm watch. Put space weather on the same wall as winds, NOTAMs, and icing, because the core will keep coughing and the sun will keep shouting. The shield will scuff in familiar places, drift a little, split sometimes, and then drift again. Our playbook isn't glamour, it's discipline. Hardware, forecasts, drills, paid forward into quiet logs. That's how you live with a noisy shield. You make the noise predictable, you budget for it, and you let the silence pay the invoice. The quiet upside, why this era is a science gift. Here's the upside nobody expects. We're alive while the machine is changing in ways we can actually measure. That's rare. For most of Earth's history, magnetic drama came and went without witnesses. We get satellites that watch the Dent split, ground stations that
hear the core's handwriting, and seismology that times the inner core's gentle backtrack. It's a live lab, and the homework counts. The data is a once-in-civilization dataset. Swarm stitched 11 years of precise vectors. Observatories add a century of drift. Ocean-bottom magnetometers are filling blue deserts on the map. Together, they've turned a static globe with neat field lines into a moving picture with edges and moods. That picture feeds models that don't just explain, they forecast. Space weather centers now fold core-aware fields into storm nowcasts, so ops teams can move minutes, not months. Cross-field gains stack quickly. Watching CME structure upstream sharpened timing for grid mitigations. Better core inversions made radiation risk maps less wrong for satellites. Aviation's dose monitors and GNSS integrity checks came out of storms, but now live in dispatch. The Dent forced software to adapt in orbit. The same patterns harden timing networks on the ground. Quiet logs across sectors feel like coincidence. They aren't. They're coordinated, because science stopped being a museum and started acting like maintenance. There's a cultural gift here too. Students aren't memorizing one world magnetic model and calling it done. They see maps breathing, forecasts updating, and ops teams treating a planet like weather.
That mindset shift, static to dynamic, bleeds outward. Volcano observatories build data assimilation. Flood models deliver hourly risk. We don't know yet becomes we'll update at 1800Z. That's not hedging, that's discipline, with a side of dark humor when the universe sends patch notes at 3 a.m. And yes, there's curiosity for its own sake. The African LLSVP's rim is a frontier that ties mantle convection to core flow. Torsional oscillations whisper 5 to 10-year beats through secular variation. Inner core growth asymmetry hints at long torque cycles. None of those fix power lines or save a CCD tomorrow, but each tightens the loop between deep earth and daily life. Every answer we pry loose moves uncertainty into schedules. Call it a live-fire class where the stakes are not annihilation, but competence. Teams already know the drill. Harden what must stay awake, mask what can sleep, widen margins on storm days, keep the core movie fresh. The upside is permission to get very good at boring victories. Rectangles of zeros that extend mission life, flat, neutral current traces on a bad solar night, a yawn in a cockpit when GPS drops for 30 seconds. We get to practice resilience before we're forced to improvise it. Your grandkids will roast us for flying with yesterday's static maps. They'll also inherit better ones because we chose continuity over heroics. Fund the successors, keep the ground network honest, and teach the habit. Measure, model, mitigate, repeat. The gift is time, lead time, trend time, and enough calendar to turn a dented shield into a managed environment. That's not luck, that's a decision, the meaning and the move. That glow on the dashboard isn't doom, it's a warranty light. The core isn't turning off tomorrow, but the shield is noisier and the sun still throws punches. Translation: higher stakes, longer timelines, and plenty of chances to look smart, or very, very offline. If this made the hidden machine feel visible, stick with us. Subscribe, then cue the deep dive on the magnetic shield to see how today's dents connect to tomorrow's storms. Let's build the playbook together before the next flare hits and those rectangles of zeros quietly save your favorite mission.